Hello, my name is Gonzalez, and today I will present you our work on a self-supervised learning framework for speaker localization with a humanoid robot. First of all, why we need sound localization in robotics? Well, sound localization is a crucial skill for human-human interaction. For example, when someone is calling you from behind, it's actually allow you to redirect your attention towards him and then engage into an interaction. And this is something that could be useful for robots because uh, it's not like vision where it's bounded by the field of view. Sound is omnidirectional and so allow the robot to have a perception of 360 degree. Furthermore, sound localization could be a solution for the cocktail party problem. In a noisy environment, the ability to identify a sound source can be used to actually filter out only the speech from this angle and discard the other one, so the noise. Robotics, several model-based approaches have been proposed to address it. For example, beamforming algorithm, correlation techniques to compute the time delay of arrival, but have some drawbacks. For example, they often need parameters fine-tuning, which in robotic can be problematic when the robot changes acoustic environment and is not is not optimal. Also, very few studies actually focus on binaural audition and rather use multi-array of microphone, and often they don't actually address strong acoustic environment where there is a lot of noise. So in this paper, the main question that we investigate is how we can develop a sound localization system for the ICAP following the how infant do. First of all, baby doesn't come in the world with an empty system. They have a lot of different mechanisms that they can use to actually guide the learning and also to guide the learning of localization of sounds. For example, they have attention bias toward faces and voices, which allow them to pay more attention to human agent. Also, they are equipped with a different method of learning where they can learn by observation and also combine different modalities. For example, cell localization has been demonstrated that vision actually help the calibration of the auditory space representation. Finally, a crucial source of information and of learning for babies is the other, which Tomasello called cultural learning, and an important um, a crucial step then for babies is to actually learn by interacting with others. And when we look closer about the typical development of sound localization in humans, we can actually see that at birth, babies are not really good at it. They can mainly discriminate between left and right position, spatial position, and also have a really long latency response. However, in only 5 months of life, they actually increase their ability with faster hand movements and also a better spatial accuracy. Finally, it's only at 5 years old that they reach adult-like ability for localizing sounds. In this paper, the main question that you try to address is to identify what is the base model that we can put into a robot, and in our case, into the ICAP, that could actually allow the ICAP to follow this kind of learning for sound localization. And to do so, we use the machine learning framework because it's suitable in the sense that as we have data and label, the machine learning system will increase its performance. And the data in robotics, we have it for free because of the different sensor of the robot and also because it is embodied in the word. The only thing that we are missing is the label. The label is computed by expert or humans afterwards, which in our case is suboptimal. What we would like rather is to actually extract the label directly from the interaction in order to do autonomous learning. And as we said before, one solution to do that is to actually use multimodal learning and to use the different sensor of the robot to actually self-supervise the other. So this is the framework that we propose. We propose to use vision to calibrate the auditory space representation of the robot. We do so by using a face detection network that allows the iCab to accurately detect face in its environment in an egocentric frame of reference, and by using a model-based sound localization system based on a Bayesian framework. The use of a Bayesian framework actually is to reproduce the innate ability of baby to localize sounds, and also with long latency, in the sense that as more evidence will come to the robot, it will be more and more confident until it reaches a certain threshold and it can decide that the sound come from the left or the right. And we use this framework in a ecological interaction where we ask participants only to speak freely to the robot. Here is a clear view of what the framework is doing during an interaction with a human. At time t0, when someone is speaking, it will take an amount of time, an average 7 to 10 seconds, until the system converge and actually choose that the sounds come from one of the predefined vague position. This trigger a head movement of the robot, and then you can use the face detection to actually identify the speaker and associate the audio recording with the spatial location. In case that the sound localization system produces a false positive, the iCap will see no face and then the audio will be discarded. We run this framework on 28 participants with collecting 4 different languages. And as you can see, we managed to have a good representation of the from field of, auditory of the robot. So the total recording was 2 hours with a sound to noise ratio of 9 decibel due to the ego noise of the robot. After pre-processing mainly by running a voice activity detector, we end up with a dataset of 90 minutes for the train set and 10 minutes for the test set by taking randomly 3 participants from the participant pool.
The backstory of the character of the Joker
Here's an
and some of the other
example
characters from other Batman movies,
of the
like the
system
Dark Knight
running in real
Rises.
time with the
Have you
robot.
seen any other Batman movies?
As you can see, as the speaker is speaking, the robot will converge toward the location, and then it can use the face detection algorithm to actually associate the audio with the face. We then design a deep learning network to actually train on those data. We use as inputs gammograms, which are a representation of the audio by passing the audio to gamma filter banks, which are closely related to the human ear. And also, gammograms have been demonstrated to be robust to noise. We then use a different stack of convolutional layer, and finally experiment with different output layer according to the discrimination of the spatial auditory space that we investigate. We try different input lengths for the network, ranging from 500 milliseconds to 2 seconds, and also 2 discretization of the space with 3 zone or 5 zone. The best result was achieved with input lengths of 2 seconds and with 3 zones. However, we can note that even going with challenging input with 500 milliseconds, the network performed reasonably well with 70% accuracy. To further demonstrate the advantage of deep learning for robotics, we actually port the trained deep networks into a new room and new robots. On the left, you have the robot that have been used for the experiment and the room in which we record all the data. And on the right, you have the new version of the iCab, which has backpack, which then produce a different ego noise, and also in a different room and with a different set of microphones. We run the network on a natural interaction and achieve a 97% of accuracy, which demonstrates both the advantage and the robustness of the deep learning networks, because no parameter fine-tuning were needed to be done, and also because it achieved really great generalization. Future work will focus on continuous learning and mainly by automatizing every process that we present in the paper into a machine learning pipeline. And also to deal with the false positive, we want to use phase locking and more precisely a correlation between the speech envelope and the mouse movement of the speaker. And finally, we want to use reinforcement learning in order to both use the visual and auditory information in order to learn the best optimal motor policy for the robot to identify an active speaker. If you have more questions about this work and want to discuss further our paper, we will be happy to answer you. Thank you very much.